Good morning to one and all. Myself Nagajyothi, working as assistant professor in Department of ECE. So in the last lectures we have seen about a transient response analysis for a first order system. So whenever we are talking a term called as a first order system, the power of S should be 1. So in this lecture we are going to discuss about transient response of a second order system for step input and the time domain specifications and related problems regarding to that topic. Coming to that, the transient response of a second order system. So in case of a second order system, the power of S should be square. So the standard transfer function for a second order system can be represented as omega n square by s square plus 2 zeta omega ns plus omega n square. This is the standard notation for a second order system, where omega n is nothing but an undamped natural frequency, and the units for the undamped natural frequency is radians per second. And zeta is a damping ratio. In general, we can define the damping ratio. It is a ratio of critical damping towards the actual damping. So depending upon the zeta value, basically the second order systems has been classified into 4 different types. If zeta value is 0, then it is called as an undamped system. If the zeta value is in between 0 and 1, it is called as an underdamped system. If zeta is equivalent to 1, it is called as a critically damped system. Similarly, if the zeta value is greater than 1, it is called as an overdamped system. So already we have seen that the second order system can be represented as omega n square by s square plus 2 zeta omega ns plus omega n square. The denominator part of a transfer function is called as a characteristic equation. So this characteristic equation is in the form of a quadratic equation. So if you compare this with the quadratic equation, ax square plus bx plus c will be getting two roots. Those two roots can be determined by using a formula of minus b plus or minus root over b square minus 4ac by 2a. In the same way, I am comparing this quadratic equation with the standard form of characteristic equation. So value of a equal to 1 and b equal to 2 zeta omega n and c equal to omega n. So if you compare this and if you solve for the roots, you'll be getting the two roots of that quadratic equation is minus zeta omega n plus or minus omega n root over zeta square minus 1. So just now I have told you that depending upon the zeta value, we are having 4 different types of system. So if you substitute this zeta value is equivalent to 0, such a system is called as an undamped system. So if I substitute this zeta value equal to 0, the first term becomes 0, and in case of the second term, I'll be getting plus or minus omega n root over zeta square minus 1. This zeta is replaced with 0, so I'll be getting plus or minus omega n root minus 1, which can be written as plus or minus j omega n. That itself indicates when the system is an undamped system, we'll be getting two roots, those two roots which are in imaginary. So when zeta is equivalent to 0, the two roots of the system is plus or minus j omega n, and the roots are purely imaginary, and the system is said to be undamped case. Similarly, when zeta is equivalent to 1, so if we substitute zeta value is equivalent to 1, we'll be getting the two roots as minus omega, and this minus omega n represents these are the real roots. These roots are real and equal. So whenever we are solving a second order equation, if the roots are real and equal, then we can say that such a system is called as a critically damped system. Similarly, if you substitute zeta is greater than 1, we'll be getting the roots as minus zeta omega n plus or minus omega n root over zeta square minus 1. In this case, we cannot able to find out exact values because the zeta value is greater than 1. We are not specifically saying it is 2, 3, 4. Depending upon the zeta value, we will be getting the roots. These roots may be real and these roots are unequal. So if we are getting real roots which are not equal, then such a systems are called as overdamped system. Similarly, if the zeta value is in between 0 and 1, such a systems is nothing but called as an underdamped system, and in this case we are calculating the roots in which the roots are complex conjugate. So if the roots are complex conjugate, the system is underdamped. If the roots are purely imaginary, it is undamped. If the roots are real and equal, it is critically damped. If the roots are real and unequal, then it is called as an overdamped. So this is all about the classification of second order systems based on the zeta value. So for example, let me assume that I have taken a system for undamped system. So for undamped system, for all these cases, we are giving the input as a step input. So this is the step input in which we are assuming it as a constant value which is having an amplitude of A, or if it is unit step, the amplitude is equivalent to 1. So in this case, if I substitute the zeta value is equivalent to 0, I'll be getting an expression of omega n square by s square plus omega n square. As I told you, the type of the input which I am giving is a step input. So r of s is equivalent to 1 by s. So I can write down that c of s expression as omega n square by s into s square plus omega n square. And as I want to represent this in terms of time domain expression, I need to use a partial expansion method. So by applying a partial fraction method, I'll be getting a by s plus b by s square plus omega n square. We are cross multiplying and we are equating the values, so that we'll be getting a is equivalent to 1 and b is equivalent to minus s. The same thing I am representing as I written previously, c of s equal to a by s plus b by s square plus omega n square. Instead of a, I am replacing here 1. Instead of b, I am replacing here as minus s. And this is in the Laplace domain. But I want the output expression in terms of the time domain. In order to convert the Laplace domain into a time domain, I need to apply the inverse Laplace transform. So the inverse Laplace transform for 1 by s is 1, and the inverse Laplace transform for s by s square plus omega n square is minus cos omega nt. So the type of the input which I am applying is a unit step input, but the output of the second order system which I'll be getting is a sinusoidal waveform, which is nothing but 1 minus of cos omega nt, and this is a response for undamped case. In the same way, we need to find out the time domain expressions for the underdamped case, critically damped case, as well as a overdamped case. But if you compare all these cases only for the underdamped case, that is for 0 less than zeta less than 1, the waveform will be taking some time to settle towards the output. So in case of only for the underdamped case, we'll be calculating the time domain specifications. So let us do one problem based on the classification. So here they have given the transfer function 4 by s square plus 2s plus 4. So this standard equation I am comparing with that of the standard equation of second order system, which is nothing but omega n square by s square plus 2 zeta omega ns plus omega n square. If you compare this, I'll be getting omega n square is equivalent to 4. So omega n is nothing but root over 4, which is equivalent to 2. Similarly, if you compare 2 zeta omega n with 2, you'll be getting zeta is equivalent to 0.5. So as the zeta value is less than 1, that itself indicates the given system is nothing but a second order system for the underdamped case. Similarly, if you see this figure, here the open loop transfer function is g of s and there is a feedback path. This feedback path value h of s value is equivalent to 1. As we know that in order to eliminate this feedback path, the overall transfer function can be written as g of s by 1 plus g of s, h of s value is 1. So this can be written as g of s is given as k by s into s plus 10. So if you substitute there, we'll be getting the transfer function as k by s square plus 10s plus k. Compare this with the standard equation, which is nothing but omega n square by s square plus 2 zeta omega ns plus omega n square. So if you compare, we'll be getting omega n square equal to k. That itself indicates omega n equal to root k. Similarly, 2 zeta omega n can be equated with 10s, and they have given zeta value is equivalent to 0.5. So 2 zeta omega n is 10 but they have given zeta as 0.5. So 2 into 0.5 into omega n, which is equal to 10. So omega n is equivalent to 10. If omega n is equivalent to 10, that itself indicates you can calculate the value of k, which is equivalent to 100. So for the given system, the value of the gain of that particular system is 100. This is how to calculate based on the zeta values as well as comparing the unknown factors of k. As I told you, in case of time domain specifications, basically we are dealing with five different components. One is delay time, rise time, settling time, peak time, and maximum overshoot. And these time domain specifications are valid only if the given system is an underdamped system. That itself indicates the value of zeta is in between 0 to 1. So if the zeta value is in between 0 to 1, then only this time domain specifications are applicable. And if you observe here, the input, as I told you that we are taking the input as step input, unit step, that itself indicates I am assuming the input as constant value as 1. But in order to reach the output from 0 to 1, it will take some time. So depending upon these times, there are different key components of the time domain specifications. So coming to the first, delay time. The delay time is nothing but it is a time required for an output to reach from 0 value to the 50% of the final value. As I told you that 50% itself indicates the input which I have taken is 1. So 50% of 1 is 0.5. So the time taken for an output to reach from 0 to 0.5 is nothing but called as a delay time. And the time response or the time domain expression for the underdamped case is that this is a generalized expression, c of t equal to 1 minus e power minus zeta omega nt by root over 1 minus zeta square into sine of omega dt plus theta. Here the time required for delay time is nothing but 0.5. By substituting this, instead of t, replace with td, and that value is nothing but 0.5. And if you simplify that, we'll be getting the delay time expression as 1 plus 0.7 zeta by omega. So just remember that what is meant by a delay time is the time required to reach the output from 0 value to the 50% of the maximum value is nothing but called as a delay time. Coming to the rise time. Rise time itself indicates the time taken for a system to reach from 0 to 100% if it is for underdamped case, or if we are dealing with a critically damped or over damped case, we are taking the consideration to reach from 10 to 90%. So in general, rise time is nothing but the time taken for an output to reach from 0 to 100% is nothing but called as an rise time. So here this is a 0. The time taken to reach 0 to maximum value is nothing but called as an rise time. In the same way, in order to calculate the rise time, we need to differentiate that c of t expression with respect to t, so that we'll be getting the peak time value is nothing but pi by omega d. Similarly, peak overshoot. If you observe the previous case, in this case, the peak overshoot is nothing but it is not only reaching to the 1, but the output is reaching beyond the value of 1. So the deviation between this and the maximum value is nothing but called as an peak overshoot. So in case of a peak overshoot, actually I need to reach the value final output is 1, but the system is not only reaching to the 1, it is reaching more than one value. The deviation between these two values, maximum reached value and the 100% value, is nothing but called as an peak overshoot. And this peak overshoot can be generally represented in terms of a percentage, and it is given by e power minus zeta pi by root over 1 minus zeta square. And coming to the last one, settling time. So here the settling time is nothing but the time required where the output will go to the constant value, means it is continuously oscillating, but after some time it will reach to the constant value, that is nothing but called as a settling time. Basically this settling time can be represented with two bands. One is 2% band and the other one is a 5% band. For the 5% band, the settling time is given by 3 by zeta omega n, which is nothing but 3t, where t is nothing but 1 by zeta omega n. And for the 2% settling time, it is given as 40. So we'll be having some numerical problems based on the time domain specifications, in which they'll be giving the value of the open loop transfer function, and they'll be asking to find out the time domain specification. So if you observe here, they have given a unity feedback system in which the g of s value is nothing but they have given as 10 by s into s plus 2. So this is an open loop transfer function. The first step is we need to find out the closed loop transfer function. The closed loop transfer function for this is, as we are having a unity feedback system, 10 by s into s plus 2 by 1 plus 10 by s into s plus 2. If you simplify this, you'll be getting as 10 by s square plus 2s plus 10. Compare this with the standard second order system, which is nothing but comparing this with omega n square. So we'll be getting omega n value as root 10. Similarly, we'll be getting a zeta value. So we got omega n value, which is root 10, which is equal to 3.162, and zeta value is 0.316. So if you observe here, the zeta value is in between 0 and 1. So we can say that this system is nothing but an underdamped system. Only for the underdamped system we are able to calculate the time domain specification. So already we have discussed the rise time formula is pi minus theta by omega d, where theta is nothing but tan inverse of root over 1 minus zeta square by zeta. So if you substitute those values, have got the rise time as 0.63 second. Similarly, we are having maximum peak overshoot percentage. Substitute those zeta values as well as the exponential values. I got that as 35.12 seconds. And specifically in case of a peak overshoot, in the given question, they have given instead of giving it as a unit step input, they have given for 12 units. That itself indicates they have given the amplitude of the step input signal as 12 units. That is the reason for the peak overshoot we need to multiply into 12 units, because amplitude is not a unit step, it is 12 volts of amplitude. And for the peak time, it is pi by omega d, and we need to calculate the settling time for the 2% band as well as for the 5% band. This is how to find out the time domain specifications for the underdamped case, specifically what is meant by a delay time, rise time, peak overshoot, as well as the settling time. Thank you.